During the Devonian period, the surface of the Earth was shaped by wide, shallow seas that spread gently across continental margins. These epicontinental waters moved slowly over stone and sediment, warmed by a stable climate and enriched by dissolved minerals carried from ancient land masses. The sea floor lay bathed in soft light, filtered through clear water columns that changed gradually with depth. There was no urgency in these oceans. Water flowed in long, unbroken patterns, guided by tides and planetary rotation, creating an environment of quiet continuity. Within these seas, life was abundant and evenly distributed. Invertebrates formed the foundation of marine ecosystems, their fossilized remains preserved in layered limestone and shale. Trilobites moved slowly across the sediment, leaving shallow traces behind them. Brachiopods anchored themselves to the sea floor, opening and closing their shells in rhythm with passing currents. Crinoids rose upward like anchored gardens, their feathered arms extended into the water to collect drifting particles. These organisms existed in balanced numbers, sustained by steady conditions that changed little across long spans of time. Above the seabed, early vertebrates moved through the water with measured motion. Jawed and jawless fishes shared these environments, occupying different levels of the water column. Their forms were shaped by gradual evolutionary pressures recorded in the fossil record, with bodies adapted for endurance rather than speed. The water supported them easily, carrying them forward without resistance. There was space in every direction, and movement followed predictable paths shaped by depth and density. Reef systems marked many regions of the Devonian seas. These reefs were built not by modern corals but by stromatoporoids and tabulate corals whose mineral skeletons formed broad, solid frameworks. Layer upon layer accumulated over time, creating low underwater rises that slowed water flow and softened wave energy. Within these reef structures, small marine organisms found shelter, while open channels between formations allowed water to circulate freely. Fossilized reef complexes show stability and longevity, indicating environments that persisted with little disruption. The water surrounding these reefs was calm and gently stratified. Warmer surface layers rested above cooler depths, forming vertical gradients that influenced where organisms lived and fed. Fine sediments settled slowly through the water, creating smooth sea floors without sharp disturbances. Chemical conditions remained stable enough to allow continuous carbonate deposition, preserving the details of shells, plates, and skeletal fragments that now rest in stone. These seas did not surge or crash, they drifted. Within these stable marine shelves lived Dunkleosteus, a large arthrodire placoderm known from well-preserved fossil remains. Its presence in the Devonian seas is confirmed by cranial armor found in marine deposits formed far from shore. Dunkleosteus moved through open waters near reef margins and continental shelves, sharing space with other placoderms and early fishes. Its environment provided ample room for steady movement and reliable access to food, supported by the dense but balanced ecosystems around it. The marine shelves themselves were broad and gently sloping. They extended far from the ancient coastlines, covered by shallow water that allowed sunlight to reach the seabed in many places. Photosynthetic activity supported food webs from below, while suspended organic matter drifted through the water column. Fossil assemblages from these regions show diverse communities preserved together, indicating long-term environmental consistency rather than sudden change. Currents in the Devonian seas moved slowly and predictably. They followed the contours of submerged landforms and reef structures, circulating nutrients without eroding the sea floor. These currents connected different habitats, allowing organisms to spread without leaving their preferred conditions. The water was neither turbulent nor still, but gently active, maintaining oxygen levels and distributing resources evenly. As time passed within the Devonian period, these seas continued their quiet work. Sediment accumulated grain by grain, skeletons settled and were buried without disturbance. Ecosystems adjusted subtly, responding to small shifts in sea level and chemistry that unfolded over immense timescales. There was no sudden motion, no sharp boundary between moments. The ocean existed as a continuous presence, holding its inhabitants within a stable and enduring world. In this ancient marine setting, everything moved slowly enough to be preserved. The Devonian seas did not rush forward. They expanded, settled, and carried life in long, unbroken rhythms. Within their layered waters and calm shelves, The foundations of later marine history were quietly laid, resting beneath the surface in steady, unchanging calm. During the Devonian period, jawed fishes became a defining presence within marine ecosystems, and among them, placoderms formed a widespread and influential group. Their remains appear consistently in marine sedimentary layers dated to this period, showing that they occupied seas across many regions of the ancient world. Placoderms are recognized by the thick, bony plates that covered the front portions of their bodies. These plates were formed from dermal bone and developed as part of the skin rather than the internal skeleton. Fossil preservation reveals their shape and arrangement with clarity, allowing their structure to be studied in detail. The armor of placoderms covered the head and thoracic region, creating a rigid protective casing. Behind this armored front, the body extended into softer tissue that was rarely preserved in fossils. The boundary between armored and unarmored regions was distinct and functional. In many placoderms, including Dunkleosteus, the armor was divided into separate units connected by joints. These joints allowed controlled movement between the head shield and the trunk shield. This construction balanced protection with flexibility and is consistently documented in articulated fossil specimens. Placoderms were among the earliest vertebrates to possess true jaws. Their jaw elements were integrated into the armored head, forming a stable framework for feeding. Unlike later fishes, placoderms did not have teeth made of enamel and dentine. Instead, their biting surfaces were composed of sharpened, bony plates. Wear patterns preserved on these plates show that they were used repeatedly and maintained functional edges over time. This feeding system was widespread among placoderms and varied in shape depending on ecological role. The Arthrodires were the most diverse order of placoderms, and Dunkleosteus belonged to this group. Arthrodires are defined by the presence of a movable joint between the head and thoracic armor. This joint allowed the head shield to lift slightly during feeding, increasing the gape of the mouth. Fossil evidence shows that this feature was present across many Arthrodire species. The consistency of this anatomy across specimens confirms that it was a stable and successful design during the Devonian. Placoderms occupied a range of marine habitats, but many Arthrodires lived in open water rather than within reef structures. Their fossils are commonly found in deposits that represent offshore environments and continental shelves. These sediments indicate calm, deeper waters away from the complex surfaces of reef frameworks. The body proportions inferred from armored remains suggest steady swimming rather than maneuvering within tight spaces. Their presence in these settings reflects an adaptation to broad, open marine zones. Within these open waters, placoderms existed alongside other early fishes, including cartilaginous and bony forms. Fossil assemblages from mid to late Devonian strata often contain large numbers of placoderm remains, indicating that they were numerically and ecologically significant. Their dominance is shown not by isolated finds, but by repeated associations across many sites. This pattern demonstrates that placoderms were not rare or marginal, but central to marine food webs of the time. The armor of placoderms also records growth and development. Lines and surface textures on the plates show stages of expansion as individuals matured. These features indicate gradual growth rather than sudden changes, matching the stable environmental conditions of Devonian seas. The thickness and density of the armor varied among species, reflecting different ecological roles. In large arthrodires, the armor was especially robust, suggesting a life spent in open water where steady protection was advantageous. Placoderms did not persist beyond the Devonian period. Their fossils disappear from the record by the end of that era, marking the conclusion of their long presence in ancient seas. During their time, however, they were among the most structurally distinctive fishes to inhabit the ocean. Their armored forms moved slowly through layered waters, shaped by evolutionary pressures that favored balance and endurance. The Devonian seas supported them fully, providing space, resources, and stability. As water flowed gently across continental shelves, placoderms continued their quiet passage through the marine world. Their armor glided beneath the surface, catching filtered light as currents passed over smooth plates of bone. They did not rush or chase in frantic motion. Their existence unfolded within a measured pace set by the ocean itself. Fossil evidence preserves this moment in Earth's history, allowing the armored fishes of the Devonian to remain part of the long, calm story of ancient seas. Dunkleosteus emerges in the fossil record during the late Devonian period, preserved within marine deposits formed beneath calm, open seas. Its remains are known primarily from cranial armor recovered from sedimentary rocks that once lay on continental shelves. These fossils occur most frequently in strata dated to the Frasnian stage, confirming the time in which this animal lived. The consistency of these findings across multiple regions shows that Dunkleosteus was a well-established component of Devonian marine ecosystems. The head of Dunkleosteus was encased in large plates of dermal bone that formed a rigid protective shield. These plates are often preserved intact, allowing their size, thickness, and articulation to be examined in detail. Surface textures and growth patterns visible on the fossils show that the armor developed gradually as the animal matured. The shape of the cranial shield was broad and compact, creating a stable structure suited to life in open water. This bony covering protected the front of the body while allowing controlled movement at its joints. Unlike later fishes, Dunkleosteus did not possess teeth formed from enamel and dentine. Instead, its jaws were equipped with sharpened bony plates that functioned as cutting surfaces. These plates grew continuously and maintained sharp edges through regular use. Fossil specimens preserve wear patterns that demonstrate repeated contact during feeding. The jaw elements were integrated directly into the armored head, forming a powerful and efficient feeding structure. This system is consistently observed across well-preserved specimens. Behind the armored head and thoracic region, the body of Dunkleosteus extended into softer tissue. This portion of the body is not preserved in the fossil record, but its presence is indicated by attachment surfaces and comparisons with related placoderms. The unarmored trunk likely supported musculature and internal organs necessary for swimming and balance. The contrast between the heavily armored front and the flexible rear created a form adapted for steady movement through water. This arrangement reflects a clear division between protection and propulsion. The overall form of Dunkleosteus shows adaptation to open marine environments rather than confined reef spaces. The broad head shield and inferred body proportions suggest a lifestyle involving sustained cruising rather than frequent maneuvering among structures. Fossil occurrences in offshore deposits support this interpretation. These sediments represent deeper shelf settings where water movement was gentle and uninterrupted. Dunkleosteus occupied these zones alongside other large placoderms and early fishes. The size of Dunkleosteus is indicated by the dimensions of its cranial armor, which ranks among the largest known for placoderms. Individual plates measure tens of centimeters across, forming a head shield of considerable mass. The thickness of the bone suggests strength and durability rather than lightness. This construction aligns with a life spent in open water where stability was favored. The animal's form did not emphasize rapid acceleration, but instead supported controlled, efficient motion. Fossil assemblages containing Dunkleosteus often include remains of other marine organisms from the same period. These associations show that it lived within complex ecosystems supported by diverse invertebrates and early vertebrates. Its presence does not appear in isolation, but as part of balanced marine communities. The repeated discovery of its fossils in similar depositional contexts indicates consistent habitat preferences. These patterns allow its ecological role to be understood without speculation. The cranial armor of Dunkleosteus also provides information about its development. Growth lines preserved within the bone record, gradual expansion over time. These features suggest a life history marked by steady growth rather than abrupt change. The environment of the late Devonian seas supported this pattern through stable conditions and reliable resources. Dunkleosteus matured within these settings, shaped by long-term interaction with its surroundings. Water conditions during the Frasnian stage were warm and supported high sea levels. These conditions created expansive shallow seas that connected marine habitats across continents. Dunkleosteus moved within these connected waters, its form suited to broad ranges rather than restricted areas. The ocean around it was layered and calm, allowing large fishes to occupy mid-water zones with ease. Its anatomy reflects this environment with clarity and precision. As Dunkleosteus emerged and persisted through the late Devonian, its presence became part of the steady rhythm of ancient seas. Its armored head passed quietly through open water, supported by a body shaped for endurance. The fossil record preserves this form without embellishment, offering a clear view of an animal adapted to its time. Within the slow currents and layered depths of the Devonian Ocean, Dunkleosteus existed as a stable and enduring presence, moving gently through a world defined by balance and continuity. The head and thoracic region of Dunkleosteus were enclosed within a framework of thick dermal armor formed from bone that developed within the skin. This armor is preserved in the fossil record with clear boundaries and defined plate margins, allowing its structure to be examined in detail. The plates fit together tightly, creating a continuous shield that covered the front portion of the body. Their arrangement reflects a design focused on stability and protection within open marine environments. The armor did not surround the entire body but concentrated mass where it was most structurally effective. The cranial armor consisted of multiple large plates joined along distinct sutures. These sutures allowed limited movement while maintaining overall rigidity. Among the most significant features was an articulated joint between the head shield and the thoracic shield. Fossil specimens preserve this joint clearly, showing how the head armor could rotate upward relative to the body. This movement increased the opening of the mouth during feeding. The jointed design demonstrates an integrated relationship between protection and function. The thickness of the armor plates varied across the head and thorax. Some regions show especially dense bone, while others are thinner but still rigid. This variation suggests careful distribution of mass rather than uniform heaviness. Fossil measurements confirm that the plates were thick enough to resist deformation. The armor did not rely on flexibility but on structural solidity. This construction suited an animal moving steadily through open water rather than navigating confined spaces. Growth patterns are visible on the outer surfaces of the armor plates. These patterns appear as lines and textures that mark stages of expansion over time. Such features are consistent across many specimens, indicating gradual and continuous growth. The bone did not form all at once but accumulated in layers as the animal matured. These growth records provide insight into the life history of Dunkleosteus without requiring inference beyond the fossil evidence. They reflect stable environmental conditions that supported sustained development. Microscopic examination of the armor reveals dense bone tissue with a well-developed network of vascular canals. Bone histology shows that the tissue was highly organized and well supplied with blood during life. This vascularization supported growth and maintenance of the armor. The density of the bone indicates strength rather than lightness. These features are consistent with other large arthrodire preserved from the Devonian seas. The internal structure of the armor shows layers of compact bone separated by zones of growth. These layers record repeated cycles of deposition. There is no evidence of rapid remodeling or frequent damage repair. Instead, the bone appears stable and long-lasting. This stability reflects a lifestyle not dominated by constant physical stress. The armor functioned as a steady framework rather than a reactive shield. The articulated nature of the armor did not compromise its strength. The joints were reinforced by overlapping surfaces and precise alignment. Fossil reconstructions show that when the head shield was lowered, the armor formed a continuous protective surface. When lifted, the movement was controlled and limited. This balance allowed feeding motions without exposing vulnerable areas unnecessarily. The design reflects careful evolutionary integration of motion and protection. The armor of Dunkleosteus was not shaped for speed-based defense. Its mass and density would have limited rapid acceleration. Instead, it provided resistance against external forces encountered in open water. The structure favored endurance and stability over agility. This interpretation aligns with the environments in which Dunkleosteus fossils are found, which represent calm marine settings rather than turbulent coastal zones. The armor complemented steady swimming rather than sudden movement. Comparisons with other placoderms show similar architectural principles. However, Dunkleosteus exhibits particularly robust development of cranial and thoracic plates. This robustness is consistently observed across specimens attributed to the genus. The repeated presence of these features across different fossil sites confirms that they were not unusual variations but standard anatomical traits. The architecture of the bone was central to the identity of the animal. The surfaces of the armor plates are often smooth, with subtle ridges marking muscle attachment points. These attachments indicate how the head and trunk were supported and moved. The relationship between muscle and bone is preserved indirectly through these features. They show that the armor was integrated into the animal's movement rather than acting as a passive shell. The bone formed part of a coordinated system supporting life in water. As Dunkleosteus moved through Devonian seas, its armor maintained form and alignment. The weight of the bone was carried evenly by the body and supported by the surrounding water. Currents passed over smooth surfaces without catching on projections. The structure did not invite turbulence, but allowed water to flow cleanly around it. This quiet interaction between bone and water defined the presence of Dunkleosteus in its environment. The architecture of bone in Dunkleosteus stands as a clear record of function shaped by ancient seas. Every plate, joint, and layer reflects adaptation confirmed by fossil evidence. The armor was neither excessive nor fragile. It was measured, dense, and stable. Within the calm, layered waters of the Devonian Ocean, this structure supported a life defined by balance, continuity, and slow movement through time. The jaw system of Dunkleosteus was formed entirely from bone, creating a feeding structure unlike that of later fishes. Fossil specimens preserve these elements clearly, allowing their shape and arrangement to be reconstructed with precision. Instead of teeth composed of enamel and dentine, Dunkleosteus bore sharpened bony plates positioned at the front of the mouth. These plates met along defined edges, forming surfaces capable of slicing and shearing. The structure was integrated directly into the armored head, uniting protection and feeding into a single anatomical system. The bony plates of the jaw were not static structures. Growth surfaces preserved on fossils show that these plates expanded gradually as the animal matured. As new bone formed along the edges, older surfaces experienced wear. This process maintained sharp cutting margins over time. The balance between growth and wear is visible in repeated patterns across multiple specimens. This continuous renewal allowed the jaw to remain functional throughout the life of the animal without replacement of individual elements. Fossil reconstructions of the skull show that Dunkleosteus possessed a wide gape angle. The joint between the head and thoracic armor allowed the upper portion of the skull to lift during feeding. When combined with the lower jaw movement, this created a large opening at the front of the head. Articulated specimens and three-dimensional reconstructions demonstrate this motion clearly. The wide gape increased access to prey within open water environments, supporting efficient feeding without rapid pursuit. Biomechanical analysis of the jaw plates and their attachment points provides further insight into function. Studies based on fossil measurements indicate that the lever mechanics of the jaw favored force over speed. Muscle attachment scars on the inner surfaces of the armor show where powerful muscles were anchored. When these muscles contracted, force was transmitted directly to the cutting plates. Relative to body size, the resulting bite force was strong and consistent. This strength arose from structure rather than sudden motion. The efficiency of the jaw system is reflected in its simplicity. Few moving parts were involved, reducing mechanical complexity. The plates acted as stable surfaces rather than flexible components. This arrangement minimized energy loss during feeding. Fossil wear patterns suggest repeated use along the same edges, indicating predictable and controlled motion. The jaw opened and closed along consistent paths shaped by bone and joint geometry. The integration of the jaw within the armored head provided additional stability. Because the jaw elements were part of the cranial structure, forces generated during feeding were distributed across the head shield. This reduced localized stress and allowed repeated use without structural failure. Fossilized plates show no evidence of frequent fracture or repair. This suggests that the design accommodated regular loading within the animal's environment. The jaw mechanism functioned smoothly within the calm waters of the Devonian seas. Feeding did not require rapid acceleration or complex maneuvering. Instead, Dunkleosteus relied on steady approach and controlled motion. The wide gape allowed capture without precise alignment, while the cutting edges completed the feeding action efficiently. This system matched the open water habitats indicated by fossil deposits. Comparisons with other arthrodire show similar jaw arrangements, though Dunkleosteus represents one of the most robust examples. The size and thickness of its plates exceed those of many related species. Despite this robustness, the fundamental mechanics remain consistent across the group. This consistency supports the interpretation that the jaw design was a successful and widespread solution within Devonian marine ecosystems. The surfaces of the jaw plates often preserve fine details. Polished areas mark repeated contact, while ridges indicate boundaries between functional zones. These details provide direct evidence of how the jaw was used. There is no indication of specialized structures beyond the cutting edges themselves. The jaw did not rely on serrations or complex shapes, but on clean, continuous edges maintained through growth. The relationship between gape angle and bite force reflects a balanced design. A wide opening did not compromise strength because force generation depended on muscle leverage rather than jaw length alone. Biomechanical models based on fossil data confirm this relationship. The result was a feeding apparatus capable of handling a range of prey sizes within the limits imposed by the environment. This versatility contributed to the ecological role of Dunkleosteus in Devonian seas. As Dunkleosteus moved through layered water columns, its jaw remained ready for steady use. Opening and closing motions followed paths defined by bone and joint surfaces. There was no excess movement, no wasted motion. The feeding cycle unfolded smoothly, guided by anatomy shaped over long spans of time. Each motion was supported by structure preserved in stone. The mechanics of the jaw reveal an animal adapted to efficiency rather than excess. Every component served a clear function supported by fossil evidence. The cutting plates, the wide gape, and the strong bite worked together within a stable framework. In the quiet openness of the Devonian Ocean, this system allowed Dunkleosteus to feed with consistency and calm. Its jaws moved as the water moved, steady and unhurried, part of the slow rhythm of ancient seas. Movement through the Devonian seas was shaped by water that flowed slowly and evenly across wide marine shelves. Dunkleosteus occupied these waters as a large arthrodire placoderm, moving within an environment defined by calm currents and layered depths. Although the tail of Dunkleosteus is not preserved in the fossil record, its form can be inferred from closely related placoderms with similar body plans. These related fossils show elongated bodies extending behind the armored head and thorax, ending in a laterally compressed tail. This general structure provides a reliable framework for understanding how Dunkleosteus moved through ancient water. The primary mode of propulsion in placoderms was lateral movement of the tail. Side-to-side motion generated forward thrust, pushing against the surrounding water in steady waves. This type of locomotion is consistent across early jawed fishes preserved from the Devonian period. Dunkleosteus, sharing the same foundational anatomy, would have relied on this pattern of movement. The motion was not abrupt or rapid, but rhythmic and continuous, suited to sustained travel through open marine spaces. The heavy cranial and thoracic armor of Dunkleosteus influenced how it swam. The mass of the armored head shifted the center of weight forward, encouraging stable, level movement rather than sharp turns or sudden acceleration. This distribution of mass would have dampened rapid changes in direction. Fossil evidence supports the interpretation that Dunkleosteus was not built for quick bursts of speed. Instead, its body plan favored control, balance, and endurance within the water column. Hydrodynamic studies based on reconstructed body shapes further support this view. Models that incorporate the known dimensions of the head armor and inferred trunk proportions show reduced drag during steady cruising speeds. The smooth contours of the armored plates allowed water to pass around the body without excessive turbulence. These reconstructions indicate that Dunkleosteus could maintain forward motion efficiently over long distances. Energy was conserved through streamlined stability rather than expended in frequent acceleration. The absence of extensive fin preservation limits detailed reconstruction, but the presence of paired fins in related placoderms is well documented. These fins likely provided additional stability and minor adjustments in orientation. Their role was not propulsion but balance, helping the animal maintain position within the water. Combined with tail-driven movement, this arrangement allowed Dunkleosteus to glide steadily through open seas. The motion would have been calm and predictable, matching the conditions of its environment. The Devonian waters inhabited by Dunkleosteus were expansive and relatively unobstructed. Fossil deposits place the animal in offshore and continental shelf settings rather than complex reef interiors. These areas offered broad prostranstva of open water where sustained swimming was more advantageous than quick maneuvering. In such environments, controlled cruising allowed efficient movement between feeding areas. The water itself supported the animal's mass, reducing the need for constant muscular effort. Lateral tail movement produces a characteristic wave that travels from head to tail. In Dunkleosteus, this wave would have been moderated by the rigidity of the armored front. Most flexion occurred in the unarmored trunk and tail region. This separation of rigid and flexible sections created a smooth transition between stability and propulsion. Fossil comparisons show this pattern consistently among arthrodires. It represents an early and effective solution to moving a heavily armored body through water. The calm nature of Devonian seas further influenced movement style. Currents were generally slow, shaped by broad continental arrangements and high sea levels. Dunkleosteus did not need to fight strong turbulence or sudden shifts in water flow. Instead, it moved within predictable patterns of circulation. This allowed steady swimming paths that followed depth contours and nutrient flows. Movement through water became part of the larger rhythm of the sea. Hydrodynamic modeling also suggests that Dunkleosteus could maintain depth with minimal effort. The balance between body mass and water displacement reduced vertical instability. Small adjustments from fins and tail orientation would have been sufficient to hold position within preferred layers of the water column. This capability supported a cruising lifestyle where energy was conserved over time. The animal did not need to rise or sink rapidly, but drifted within stable zones. The relationship between movement and feeding was closely linked. Controlled swimming allowed Dunkleosteus to approach prey without sudden disturbance. Wide gape and strong jaw mechanics complemented this slow approach. There was no need for rapid pursuit when steady movement brought the animal into range. Fossil evidence of feeding wear aligns with this interpretation, showing repeated use rather than sudden impacts. Movement and feeding formed a coordinated system. The tail, though not preserved, played a central role in this system. Its lateral sweeps translated muscular effort into forward motion. The rhythm of these sweeps would have been even and measured. Each movement pushed water aside and backward, carrying the body forward with minimal waste. This form of propulsion is efficient at moderate speeds, ideal for cruising through open water. Dunkleosteus fit this pattern well. The expansive nature of its habitat meant that long-distance movement was likely common. Fossil distribution across wide geographic areas indicates that Dunkleosteus occupied large ranges within the Devonian seas. Steady swimming supported this distribution, allowing individuals to traverse broad shelf regions over time. There is no evidence of localized restriction to small areas. Movement through water connected different parts of its environment seamlessly. As Dunkleosteus passed through layered waters, its body moved in harmony with surrounding currents. Armor remained aligned, tail motion remained consistent, and balance was maintained without strain. The water carried sound away, and motion left little trace behind. Fossil evidence captures only the structure, not the movement itself, yet that structure speaks clearly. It reveals an animal shaped for calm, sustained travel through ancient seas. Movement through ancient water defined the daily existence of Dunkleosteus. Every aspect of its form supported steady propulsion rather than sudden change. Hydrodynamic balance, tail-driven motion, and heavy armor worked together as a unified system. Within the quiet openness of Devonian oceans, Dunkleosteus moved without urgency. Its path followed the slow, continuous flow of the sea itself, drifting forward through deep time in measured, unbroken motion. Dunkleosteus occupied regions of the Devonian seas that lay beyond the shallowest waters, moving through mid-water zones and deeper continental shelves. Fossil remains attributed to this animal are consistently recovered from marine deposits formed away from coastal margins. These sediments reflect environments where water depth increased gradually and conditions remained stable over long periods. The distribution of fossils across such deposits indicates a preference for open shelf settings rather than near-shore shallows. Within these zones, the water column extended downward in calm layers. Light penetrated Devonian seas differently than in later oceans, yet it was sufficient to support structured marine ecosystems. Clear water allowed sunlight to filter through upper layers, gradually diminishing with depth. This created distinct vertical zones where different organisms lived and fed. Fossil assemblages show that these layers were occupied consistently, forming stable ecological arrangements. Dunkleosteus moved within these illuminated and dimming waters, remaining below the brightest surface levels but above the darkest depths. The absence of modern plankton groups did not limit productivity in these seas. Devonian oceans supported food webs built from invertebrates, early fishes, and microscopic life known from fossilized remains and chemical signatures. Organic material circulated through the water column in a steady manner. This circulation allowed energy to pass from lower levels upward without sudden surges. Dunkleosteus existed within this balanced system, relying on food availability that remained constant over time. Sediment records from the late Devonian indicate stable oxygen conditions within shelf environments. Fine laminations in shale and limestone suggest slow deposition without signs of frequent disturbance. The chemistry preserved in these layers reflects waters that were well oxygenated at the depths Dunkleosteus inhabited. Such stability supported long-lived communities with predictable patterns of life. The absence of abrupt shifts in sediment type points to continuity rather than episodic stress. Within these oxygenated waters, the environment remained quiet. Currents moved gently along the contours of the seafloor, guided by broad continental shapes. There were no steep gradients or abrupt barriers in these shelf zones. Water flowed evenly, connecting habitats across wide areas. Dunkleosteus traveled through this connected space, its movement supported by the calm nature of the surrounding sea. Light diminished gradually as depth increased, shaping how organisms were distributed. Fossils of invertebrates and fishes show consistent placement within these layers, indicating long-term stability. Dunkleosteus occupied depths where light was present but softened, creating a muted underwater environment. Vision in these conditions did not require sharp contrast, only steady illumination. The animal's presence in such zones reflects adaptation to moderate light rather than bright surface glare. The layered structure of Devonian seas allowed multiple ecosystems to coexist vertically. Nearer the surface, light supported primary productivity. Below, organic material drifted downward, sustaining mid-water organisms. Deeper still, sediment settled slowly onto the sea floor. Dunkleosteus moved through the middle of this system, where resources passed steadily and conditions changed little. Fossil evidence shows no sign of frequent vertical migration beyond these preferred layers. The deeper shelf zones were not isolated or stagnant. Water exchange occurred continuously, maintaining oxygen and distributing nutrients. Sedimentary features show that these processes operated over long spans of time without interruption. The resulting environment was neither still nor turbulent, but gently active. Dunkleosteus existed within this motion, its life unfolding alongside slow currents and settling particles. Food webs in these depths were diverse yet balanced. Invertebrates formed the base, while early vertebrates occupied higher levels. Fossil associations demonstrate repeated co-occurrence of the same groups, suggesting stable interactions. Dunkleosteus was part of this network, not separated from it. Its fossils appear alongside those of other marine organisms adapted to similar depths, reinforcing the picture of a connected ecosystem. The quiet nature of these environments is reflected in the preservation of fossils themselves. Many specimens show minimal signs of transport or damage, indicating they settled gently after death. Fine sediments covered remains gradually, protecting them from disturbance. This mode of preservation mirrors the calm conditions of the living environment. Dunkleosteus inhabited waters where both life and burial occurred without abrupt change. Light conditions also influenced the appearance of the water itself. In mid-depth zones, illumination was diffuse, spreading evenly rather than forming sharp beams. This created a consistent visual environment that changed slowly with depth and time of day. Dunkleosteus moved within this muted light, its form outlined softly against the surrounding water. Fossil evidence does not suggest adaptation to extreme darkness or intense brightness. The continuity of Devonian shelf environments allowed species to persist over extended intervals. Sediment layers containing Dunkleosteus span long stretches of geological time without major interruption. This continuity indicates that the depths and light conditions it inhabited remained suitable across generations. The ocean did not shift suddenly around it. Instead, conditions drifted gradually, allowing stable patterns of life. Depth also influenced temperature, though changes were moderate within shelf waters. Warm surface conditions extended downward through much of the water column. This thermal stability supported metabolic consistency among marine organisms. Dunkleosteus existed within these tempered waters, avoiding extremes. Fossil distribution aligns with regions where temperature gradients were gentle rather than abrupt. As Dunkleosteus moved through mid-water and deeper shelf zones, it followed paths shaped by depth and light. Its presence did not disturb the environment, nor did the environment demand sudden response. Everything unfolded at a measured pace. The water above filtered light, the water below settled into shadow, and between them lay a space of quiet continuity. The Devonian Sea at these depths was a place of endurance rather than change. Oxygen remained available, food flowed steadily, and light faded gradually. Dunkleosteus inhabited this zone as part of its natural order. Fossil evidence preserves this setting without embellishment. It shows an ancient ocean defined by balance, where depth and light combine to create a calm and lasting world. The Devonian seas that held Dunkleosteus were not empty spaces, but living waters shared by many forms of life. Fossil assemblages from the same marine strata record a wide range of organisms existing together within these environments. Their remains appear repeatedly in association, preserved within limestone and shale that once settled slowly on the sea floor. This repeated co-occurrence shows that these animals lived side by side within stable ecosystems. Dunkleosteus was one presence among many, moving through a sea already full of life. Ammonoids were common inhabitants of these Devonian waters. Their coiled shells are preserved in great numbers, often found in the same deposits as placoderm remains. These cephalopods occupied open water, drifting and swimming through mid-water zones. Their shells show consistent growth patterns and chamber structures, recording steady life histories. Ammonoids formed an important part of marine food webs, linking smaller organisms to larger predators. Their presence contributed to the layered complexity of the sea. Trilobites also remained abundant during much of the Devonian period. Fossils show them resting on or moving across the sea floor, particularly along shelf regions. Their segmented bodies and compound eyes are preserved with remarkable clarity. Trilobite diversity declined toward the later Devonian, but many forms still thrived alongside placoderms. They occupied benthic zones below the waters where Dunkleosteus moved, forming a foundation for the ecosystem below. Early sharks shared these seas as well, represented by cartilaginous fishes preserved mostly through teeth and fin spines. These fossils occur in the same layers as Dunkleosteus armor, confirming their coexistence. Early sharks occupied a range of depths and feeding roles, moving through open water and along the sea floor. Their bodies were flexible and lightly built compared to placoderms. Together, these different fish groups filled overlapping but distinct ecological spaces. Lobe-finned fishes were another important component of Devonian marine life. Their fossils show robust fins supported by internal bones, adapted for maneuvering within water. These fishes inhabited both open marine settings and areas closer to the sea floor. Their presence alongside placoderms and early sharks reflects a diverse vertebrate community. Lobe-finned fishes contributed to the balance of marine ecosystems through steady, sustained activity rather than rapid change. Reef edges marked important transition zones within the Devonian seas. Stromatoporoid and coral reefs formed broad structures that gradually gave way to open basins. Fossil evidence shows that placoderms, including Dunkleosteus, often occupied areas beyond the reef framework rather than within it. These edge zones allowed movement between structured and open environments. Water flow slowed near reefs and became more uniform farther out, creating varied but connected habitats. Within these connected spaces, interactions occurred without domination by a single species. Fossil assemblages show a mixture of organisms across different sizes and feeding roles. No single group appears in all zones at all depths. Instead, species were distributed according to their adaptations and environmental preferences. Dunkleosteus did not replace or exclude other large fishes, but existed alongside them within shared waters. The balance of these ecosystems is reflected in the consistency of fossil layers. Many Devonian deposits show repeated sequences of the same organisms preserved together. This pattern suggests long-term stability rather than frequent disruption. Species interactions followed predictable paths shaped by anatomy and environment. Energy moved through the system gradually, from smaller organisms upward. The sea functioned as a continuous network rather than a hierarchy dominated by one form. Open basins beyond reefs provided space for larger fishes to move freely. Fossil evidence places Dunkleosteus in these areas, where wide water columns allowed steady swimming. Ammonoids and early sharks also occupied these basins, each using the space differently. The absence of physical barriers allowed overlap without constant competition. Movement through these zones followed the slow rhythms of the sea. Benthic organisms, including trilobites and other invertebrates, remained below, rarely intersecting directly with large pelagic fishes. This vertical separation reduced conflict and allowed multiple communities to exist simultaneously. Fossil preservation supports this structure, showing organisms preserved where they lived rather than mixed chaotically. The sea was layered not only by depth and light, but by life itself. The Devonian Ocean supported diversity through stability. Sea levels remained high and continental shelves were broad. These conditions created expansive habitats that could support many species at once. Dunkleosteus was adapted to one part of this system, not all of it. Its coexistence with other organisms reflects a marine world organized by gradual specialization rather than dominance. Fossil sites capturing these communities often preserve delicate structures such as thin shells and articulated exoskeletons. This preservation indicates calm conditions at the time of burial. The same calm that allowed these organisms to live together also allowed them to be recorded together in stone. The environment did not favor chaos, but continuity. Interactions within this sea were shaped by movement, feeding, and space, not by constant conflict. Organisms followed paths defined by depth, structure, and resource availability. Dunkleosteus moved through open waters while others remained closer to the bottom or drifted through mid-water layers. Each form occupied its place without overwhelming the rest. The presence of many life forms within the same strata shows that the Devonian Sea was rich but balanced. Diversity did not lead to instability. Instead, it supported resilience across long spans of time. Fossil evidence captures this balance clearly, without gaps or abrupt transitions. Life flowed steadily through these ancient waters. As Dunkleosteus passed through reef edges and open basins, it remained part of a wider living system. Around it moved ammonoids. Below it rested trilobites, and alongside it swam early sharks and lobe-finned fishes. No single presence defined the sea. Together, these organisms formed a calm, interconnected world, drifting through the Devonian Ocean in quiet continuity. Feeding within the Devonian seas occurred as part of a stable and interconnected marine system. Dunkleosteus existed within this system as one participant among many, drawing nourishment from organisms already integrated into the ocean's structure. Fossil evidence provides clear insight into its feeding behavior through preserved bite marks and associated remains. These records show interaction rather than disruption, confirming that feeding followed established pathways within the ecosystem. Energy moved through the sea in measured steps, shaped by anatomy and environment rather than excess. Bite marks preserved on the armor of other placoderms provide direct evidence of predation. These marks are found on fossilized cranial and thoracic plates, showing clean edges consistent with contact from bony cutting surfaces. The shape and placement of these marks align with the jaw structure of Dunkleosteus. Their presence across multiple fossil sites confirms that such interactions occurred repeatedly. This evidence grounds feeding behavior firmly in the fossil record without the need for inference beyond what is preserved. In addition to armored fishes, Dunkleosteus fed on soft-bodied organisms. While soft tissues themselves are rarely preserved, their role in Devonian food webs is well documented through indirect evidence. Fossil assemblages include organisms with less robust skeletons that occupied mid-water and benthic zones. The jaw structure of Dunkleosteus, with broad cutting plates and a wide gape, was capable of processing such prey. This versatility allowed it to draw energy from multiple sources within the marine system. Feeding did not occur in isolation. Dunkleosteus shared its environment with other predators and consumers, each occupying overlapping but distinct roles. Fossil distributions show no collapse or imbalance associated with its presence. Instead, ecosystems remained diverse and persistent across long spans of time. The continued coexistence of placoderms, early sharks, and other fishes indicates that predation pressures were absorbed by the system as a whole. Energy flowed steadily through trophic layers in the Devonian Ocean. Primary producers supported invertebrates, which in turn sustained higher-level consumers. Dunkleosteus occupied an upper position within this structure, drawing energy upward without severing the flow below. Fossil evidence shows that prey species persisted alongside predators rather than disappearing abruptly. This pattern reflects a system regulated by availability and reproduction rather than unchecked consumption. The armor of placoderms served as both protection and record. Bite marks preserved on these surfaces provide rare insight into feeding interactions between large fishes. The fact that such armor was bitten but not always destroyed suggests encounters that did not always result in complete consumption. This variability reflects realistic feeding dynamics rather than constant success or failure. The ecosystem accommodated these interactions without destabilization. Soft-bodied prey contributed to the diet as well, though their role is understood through broader fossil context. Devonian seas supported abundant invertebrate life, including forms without heavy skeletons. These organisms formed an important link between lower and higher trophic levels. Dunkleosteus, with its efficient jaw mechanics, could process such prey as part of its feeding routine. This adaptability supported consistent energy intake. The feeding behavior of Dunkleosteus unfolded within calm marine settings. There is no evidence of rapid pursuit or chaotic feeding events preserved in the fossil record. Instead, wear patterns on jaw plates suggest repeated, controlled use. Feeding likely involved steady approach and efficient processing rather than sudden bursts of activity. This aligns with its inferred movement style and habitat preferences. Over millions of years, the Devonian marine system maintained balance. Fossil layers show continuity of species assemblages across time. Dunkleosteus appears within these layers without signs of causing widespread disruption. Its presence coincides with stable populations of prey species and other predators. This long-term coexistence indicates that feeding pressures were distributed and sustainable. The structure of trophic layers remained intact throughout much of the Devonian period. When changes occurred, they unfolded gradually and affected multiple groups simultaneously. Dunkleosteus participated in this system without altering its fundamental organization. Fossil evidence supports a view of feeding as part of a broader ecological rhythm. Energy moved upward, was transferred, and returned to the system through decay and recycling. The stability of this feeding web is reflected in the geological record. Sediments accumulated slowly, preserving organisms in their living associations. There are no signs of sudden mass mortality linked specifically to predation by Dunkleosteus. Instead, the record shows continuity and repetition. Life and feeding followed patterns that endured across vast stretches of time. Interactions between predator and prey were shaped by anatomy rather than aggression. The cutting plates of Dunkleosteus met the armor or bodies of prey in ways dictated by form and movement. These interactions were mechanical and functional, not chaotic. Fossil marks preserve this relationship with clarity. They show contact, pressure, and release, all within the bounds of normal ecological activity. Feeding within the Devonian web supported long-term stability. Each organism drew what it needed without exhausting the system. Dunkleosteus occupied its place without expanding beyond it. Fossil evidence consistently shows a marine world capable of sustaining large predators alongside diverse prey. This balance did not depend on any single species. As energy flowed through the Devonian seas, it followed paths shaped by evolution and environment. Dunkleosteus was one conduit among many, transferring energy upward through its feeding. The ocean absorbed this activity without disturbance. Fossils preserve a picture of continuity where feeding was part of the sea's slow pulse. Within this ancient web, Dunkleosteus fed, grew, and moved as part of a living whole. Its interactions left marks in stone but did not fracture the system. The Devonian Ocean remained stable, layered, and enduring. Feeding occurred quietly, integrated into a marine world that sustained itself over millions of years through balance and steady flow. The growth and lifespan of Dunkleosteus are recorded quietly within the structure of its armor. Fossilized plates preserve growth rings that formed as layers of bone were added over time. These rings appear as subtle bands within the dermal bone, similar in pattern across multiple specimens. Their regular spacing indicates steady growth rather than sudden spurts. This pattern reflects a life shaped by consistency rather than rapid change. The presence of growth rings shows that Dunkleosteus did not reach full size quickly. Instead, its development unfolded gradually over many years. Each layer of bone represents a period of continued living within stable environmental conditions. The armor expanded outward as the animal matured, maintaining its overall form while increasing in size. Fossil evidence does not support rapid juvenile growth followed by early maturity. The process was slow and sustained. Studies of placoderm bone histology show organized deposition rather than irregular growth. In Dunkleosteus, this organization is especially clear in cranial and thoracic plates. The bone tissue reveals cycles of growth that correspond to environmental rhythms. These cycles suggest long lifespans measured in decades rather than short intervals. The armor records time passing quietly, layer by layer. The likelihood that Dunkleosteus lived for several decades is supported by comparisons with other large placoderms showing similar growth patterns. Larger individuals display more growth rings, indicating longer periods of accumulation. There is no evidence of abrupt cessation of growth early in life. Instead, growth continued gradually until maturity was reached. This slow maturation aligns with stable marine environments that could support long-lived organisms. Seasonal stability in the Devonian seas contributed to these extended life cycles. Sediment records show consistent deposition with limited signs of environmental disruption. Water temperatures remained relatively stable, and oxygen levels were sufficient across shelf zones. These conditions reduced stress on marine organisms. Dunkleosteus lived within an environment that allowed predictable growth year after year. The steady availability of food also supported long lifespans. Fossil evidence indicates stable food webs with persistent prey populations. Dunkleosteus did not depend on unpredictable resources. Instead, it fed within a system that renewed itself continuously. This reliability allowed energy to be allocated toward maintenance and gradual growth rather than rapid reproduction or early maturation. As Dunkleosteus aged, its armor thickened and expanded without losing structural integrity. Growth rings show that new bone integrated smoothly with older layers. There are no signs of frequent damage or repair that would indicate constant physical stress. The armor remained functional throughout the animal's life. This durability reflects both the quality of bone tissue and the calm conditions of its habitat. Slow maturation also influenced reproductive timing. While direct evidence of reproduction in Dunkleosteus is limited, related placoderms show delayed maturity consistent with long lifespans. Growth patterns support this framework. Individuals invested time in development before reaching full adult form. This strategy fits environments where survival rates were high and conditions remained stable over long periods. The predictable nature of the Devonian marine environment is reflected in the uniformity of growth patterns across different fossil sites. Dunkleosteus specimens from various regions show similar ring spacing and bone structure. This consistency suggests that environmental conditions were broadly similar across its range. Growth was not localized to exceptional conditions but occurred wherever the species lived. Life unfolded at a measured pace. Dunkleosteus did not rush through its development. Each year added another thin layer of bone, quietly recording the passage of time. These layers accumulated as the animal moved through open water, fed and maintained its place within the ecosystem. The armor became a record of lived years, preserved long after the sea itself changed. The long lifespan of Dunkleosteus contributed to ecological stability. Long-lived predators exert consistent pressure rather than sudden spikes. This consistency helps maintain balance within food webs. Fossil evidence shows no abrupt shifts in prey populations linked to its presence. Instead, predator and prey coexisted within a regulated system shaped by time. Environmental predictability reduced the need for rapid life strategies. Dunkleosteus did not need to mature quickly or reproduce early to ensure survival. The seas provided continuity. High sea levels and broad shelves created extensive habitats that remained suitable across generations. Growth could proceed slowly without risk of sudden habitat loss. The armor's growth rings also suggest periods of slower and faster deposition, likely corresponding to subtle environmental cycles. These variations remain within a narrow range, indicating moderation rather than extremes. The environment changed gently, allowing organisms to adjust without interruption. Dunkleosteus responded by maintaining steady development rather than altering its life history. As decades passed, Dunkleosteus reached full size, carrying armor shaped by years of incremental change. Its mature form represented the accumulation of time rather than a single event. The animal continued to live within the same broad conditions that supported its growth. There was no sharp boundary between youth and adulthood, only gradual transition. The fossil record preserves individuals at different stages of growth. Smaller specimens show fewer growth rings, while larger ones display many. Together, they outline a lifespan that extended across significant time. This range of sizes within the same deposits suggests overlapping generations living together. The population structure was stable rather than episodic. Growth did not stop abruptly at maturity. Even adult individuals show continued bone deposition. This indicates ongoing maintenance and adaptation rather than static form. The armor remained responsive to the animal's body, adjusting slowly as needed. This adaptability supported long-term survival. The Devonian seas rewarded patience. Dunkleosteus lived within an environment that did not demand haste. Its growth reflected this rhythm, bone layered upon bone year after year without urgency. The lifespan extended quietly through time, supported by stable waters and reliable resources. In this slow unfolding of life, Dunkleosteus matured within predictable conditions. Its armor recorded the passing years, its body adapted gradually, and its existence blended into the long continuity of the Devonian Ocean. Growth and lifespan were not marked by extremes, but by balance. The fossil record preserves this balance clearly, offering a calm reflection of time moving steadily through ancient seas. Reproduction among placoderms is recorded through rare and valuable fossil evidence preserved from the Devonian period. Certain placoderm fossils show clear anatomical structures associated with internal fertilization. These structures are preserved in articulated specimens and have been studied in detail, confirming this reproductive mode within the group. Dunkleosteus belongs to the arthrodire placoderms, and its placement within this framework is based on shared anatomical characteristics. This reproductive strategy unfolded within calm marine environments that supported slow and stable life cycles. Internal fertilization represents an important aspect of placoderm biology. Fossil specimens of related placoderms preserve paired claspers, structures used to transfer reproductive material. These features are unambiguous in their function and are not present in earlier jawless fishes. Their presence confirms that fertilization occurred within the body rather than externally in the water. Dunkleosteus, sharing close anatomical relationships with these placoderms, is understood within the same reproductive system. This framework reflects a controlled and protected approach to reproduction. The use of internal fertilization reduced reliance on open water conditions during the earliest stages of development. Instead of releasing reproductive cells into the surrounding sea, development began within the body. This increased the likelihood of successful reproduction within stable environments. Devonian seas provided the calm conditions needed for such a strategy to function effectively. The ocean did not require rapid or seasonal spawning events driven by turbulence or extremes. Juvenile placoderms are represented in the fossil record by smaller armor plates and partial remains. These fossils are often found in shallower marine deposits compared to those of large adults. This distribution suggests that younger individuals occupied different zones within the marine environment. Shallow waters along continental shelves provided suitable conditions for early growth. These areas offered calmer currents and abundant resources without the demands of open, deeper waters. Occupying shallower waters during early life reduced exposure to physical stress. Fossil evidence indicates that these zones experienced gentle water movement and consistent conditions. Fine sediments accumulated slowly, preserving delicate remains. Juveniles developed within these environments before moving into deeper waters as they matured. This separation of life stages supported survival without disrupting broader ecosystems. The Devonian marine environment supported this reproductive pattern through its stability. High sea levels created extensive shelf areas with gradual depth changes. These shelves allowed organisms to shift habitats over time without encountering abrupt boundaries. Juveniles could remain in protected zones while adults occupied deeper regions. Fossil distributions reflect this arrangement consistently across different geographic locations. Placoderm reproduction did not rely on mass spawning events. Instead, internal fertilization supported smaller numbers of offspring developing under controlled conditions. This approach aligned with long lifespans and slow maturation. Dunkleosteus, with its extended growth period, fit within this reproductive rhythm. The environment supported quality of development rather than quantity of offspring. The calm Devonian seas were well suited to such cycles. Sedimentary records show limited evidence of seasonal extremes or rapid environmental shifts in many shelf regions. Temperature and oxygen levels remained relatively consistent. These conditions reduce stress during reproductive and developmental stages. Dunkleosteus lived within a system that favored continuity across generations. Fossil evidence does not indicate specialized nesting structures or parental care beyond reproductive anatomy. Development proceeded within environmental conditions rather than constructed shelters. Juveniles grew within natural marine settings shaped by water depth and resource availability. This simplicity reflects ecosystems that did not require complex reproductive adaptations to survive. The separation between juvenile and adult habitats also reduced competition for resources. Younger individuals occupied different feeding zones than larger adults. This reduced direct interaction between life stages. Fossil assemblages support this structure by showing size variation across depositional environments. Such distribution allowed populations to persist without internal pressure. Internal fertilization also reduced the need for precise timing with environmental cycles. Reproduction was less dependent on external conditions such as water temperature spikes or current changes. This flexibility supported long-term population stability. Dunkleosteus reproduction unfolded within predictable conditions that changed slowly over geological time. The reproductive cycle integrated smoothly into the broader marine system. Energy invested in reproduction did not disrupt feeding patterns or growth. Fossil evidence shows no abrupt population booms or collapses linked to reproductive behavior. Instead, placoderms remained present across long stratigraphic intervals. Dunkleosteus followed this pattern, appearing consistently in late Devonian deposits. Juvenile development within calmer waters also supported gradual growth. Smaller armor plates show growth features similar to those of adults, indicating continuous development. The same steady patterns observed in mature individuals began early in life. This continuity reflects an environment that supported organisms from early stages through adulthood without sharp transitions. The Devonian Ocean did not impose urgency on reproduction. There was time for development, movement between habitats, and integration into adult roles. Dunkleosteus matured within this framework, shaped by reproductive strategies inherited from its lineage. The fossil record preserves these patterns without interruption, allowing them to be recognized clearly. As generations passed, this reproductive cycle repeated quietly. Internal fertilization, juvenile development in shallower waters, and gradual movement into deeper zones formed a consistent pattern. The sea accommodated these stages without strain. Each phase flowed into the next as part of a larger rhythm shaped by stability. The calm waters of the Devonian supported reproduction without spectacle or disturbance. There were no sudden gatherings or violent movements associated with spawning. Life began quietly and continued steadily. Dunkleosteus entered the world within this gentle system, supported by conditions that favored endurance. Fossil evidence anchors this understanding firmly in preserved anatomy and distribution. Reproductive structures, growth stages, and habitat use align across placoderms. Dunkleosteus fits within this established framework. Its reproductive cycle reflects adaptation to an ocean defined by continuity. Within the quiet waters of the Devonian seas, reproduction unfolded as a measured process. Each generation followed the last without disruption. Juveniles grew where conditions were gentle. Adults moved where space was broad, and the cycle continued. The fossil record preserves this calm repetition, showing a marine world where life began and matured in balance, drifting steadily through deep time. During the late Devonian, Earth's climate remained broadly warm, shaped by continental arrangements and atmospheric conditions recorded in sedimentary rocks. Evidence from isotopic studies and fossil distributions indicates minimal polar ice during this interval. With little permanent ice at high latitudes, global temperatures stayed relatively even. This warmth reduced strong thermal gradients between regions. Oceans absorbed and redistributed heat gradually. Such conditions created predictable marine environments across wide areas. The climate did not fluctuate abruptly. Instead, it supported continuity over long spans of time. Marine organisms experienced stability rather than seasonal extremes. This climatic background framed all Devonian ocean life. High sea levels characterized the late Devonian world. Geological evidence shows that large portions of continents were submerged beneath shallow epicontinental seas. These waters spread gently across continental interiors, connecting distant marine regions. Shorelines shifted slowly, not suddenly. The expansion of shallow seas increased habitat availability for marine organisms. Warm temperatures maintained these flooded conditions over extended periods. There is no evidence of rapid sea level collapse during much of this time. Instead, marine settings persisted. These expansive seas supported diverse communities. Dunkleosteus occupied parts of these broad, shallow marine systems across stable late Devonian shelves worldwide for long durations. Carbonate deposition dominated many marine sediments during the late Devonian. Limestone and related carbonate rocks accumulated as skeletal material settled on seafloors. Organisms with calcareous structures contributed steadily to sediment formation. These deposits indicate warm, clear waters favorable to carbonate production. Fossil reefs and platform carbonates record prolonged stability. The rate of deposition suggests slow accumulation without frequent disruption. Such sediments preserve detailed fossil assemblages. They also record chemical conditions of seawater. Carbonate dominance reflects low terrigenous input in many regions. These geological features reveal a calm, enduring marine climate across extensive Devonian shelf environments globally preserved today widely. Warm climatic conditions supported long-term ecosystem stability in Devonian oceans. Stable temperatures reduced stress on marine organisms. Predictable conditions allowed life cycles to proceed without interruption. Fossil assemblages show continuity of species across stratigraphic layers. There is little evidence of frequent climatic shocks during this interval. Instead, ecosystems adjusted gradually to slow changes. Energy flow through marine food webs remained consistent. Primary production supported invertebrates and vertebrates alike. Such stability allowed large fishes to persist over time. Dunkleosteus existed within this steady climatic framework throughout much of the late Devonian period across multiple oceanic regions worldwide, continuously recorded geologically. Minimal polar ice influenced ocean circulation patterns during the late Devonian. Without large ice sheets, sea level remained elevated. Thermal gradients between equatorial and higher latitude waters were reduced. This promoted broad, slow-moving ocean circulation. Heat distribution remained even across marine basins. Such circulation limited extreme temperature shifts. Fossil evidence supports widespread warm water conditions. Marine species occupied wide geographic ranges. Dunkleosteus fossils appear across different regions, reflecting connected seas. The climate allowed dispersal without major barriers, reinforcing long-term ecological stability across Devonian continental shelves and epicontinental seas for millions of years, continuously documented stratigraphically worldwide in sediments. High sea levels expanded shallow marine habitats that were important for marine productivity. Shallow seas allowed sunlight to reach the sea floor in many areas. This supported photosynthetic activity recorded indirectly through fossil assemblages. Carbonate platforms developed extensively under these conditions. Sedimentological evidence indicates gentle water movement. Fine-grained sediments settled slowly. These habitats were not transient, they persisted across long geological intervals. Dunkleosteus utilized portions of these environments as part of its range. The climate maintained these habitats without abrupt disruption during the late Devonian period, supporting stable marine ecosystems across broad continental interiors globally preserved today in rock. Atmospheric conditions during the late Devonian contributed to greenhouse warmth. Geological proxies indicate elevated levels of atmospheric carbon dioxide. This enhanced heat retention at the surface. Warm oceans absorbed this heat efficiently. The resulting climate lacked strong seasonal extremes in many regions. Such conditions favored slow-growing, long-lived marine organisms. Fossil evidence aligns with extended lifespans observed in placoderms. Dunkleosteus benefited from this environmental consistency. The climate reduced pressures associated with rapid environmental change. Stability allowed marine communities to remain structured and persistent over extended Devonian timescales, recorded consistently in sedimentary sequences worldwide without interruption or collapse events. Climate also influenced chemical conditions of seawater. Warm temperatures promoted carbonate saturation in marine environments. This chemical balance supported shell and skeleton formation. Fossil records show widespread preservation of calcareous organisms. Stable chemistry reduced dissolution of skeletal material. Oxygen levels remained sufficient in many shelf seas. Geochemical indicators support well-oxygenated conditions. Such chemistry supported diverse animal communities. Dunkleosteus lived within waters that maintained consistent chemical properties. These properties changed gradually, reinforcing long-term environmental continuity throughout the late Devonian period across extensive marine basins and continental shelves documented in stratigraphic records globally for millions of years without abrupt shifts. The Devonian climate did not operate in isolation from geological processes. Continental positions influenced ocean circulation and climate distribution. Broad tropical regions dominated continental arrangements. These positions increased solar heating across shallow seas. Geological reconstructions confirm these configurations. Warm climates persisted as continents remained near equatorial latitudes. The resulting environmental conditions favored marine expansion. Dunkleosteus existed within these paleogeographic settings. Its fossils align with predicted warm water regions. Climate and geography together shaped the Devonian marine world across long durations of time, supporting ecological stability and persistence recorded in marine sediments worldwide during the late Devonian period, clearly preserved today. Within this climate regime, Dunkleosteus thrived without facing abrupt environmental stress. Warm temperatures, high sea levels, and stable chemistry supported its life history. The ocean remained expansive and predictable. Ecosystems persisted with continuity across generations. Fossil evidence shows Dunkleosteus present throughout suitable intervals. Its distribution matches warm, shallow marine settings. The climate did not drive rapid adaptation or decline during this time. Instead, it allowed persistence. The Devonian seas provided reliable conditions. This climatic stability underpinned the long success of Dunkleosteus within late Devonian oceans, sustained by global warmth and elevated sea levels for millions of years, consistently recorded geologically. As the late Devonian continued into the later Frasnian stage, the marine world began to change in quiet and gradual ways. These changes did not arrive suddenly, but unfolded over long intervals recorded carefully in stone. Sediment layers from this time show subtle shifts in composition and structure. Grain sizes vary, chemical signatures adjust, and fossil assemblages alter their balance. Together, these records reveal an ocean beginning a slow transformation beneath an otherwise calm surface. One of the most significant changes involved oxygen levels within certain marine basins. Geochemical evidence preserved in sedimentary rocks shows that oxygen availability fluctuated in some deeper and more restricted environments. These fluctuations were not uniform across all seas. Many shelf areas remained well oxygenated, while others experienced intervals of reduced oxygen. This variation created differences between regions rather than a single global condition. The ocean became more heterogeneous in its internal structure. In basins where oxygen levels declined, sediment layers often show darker coloration and finer lamination. These features indicate slower water circulation and reduced mixing. Organic material accumulated more readily in these settings. Fossils preserved in such layers are often more complete, reflecting calmer bottom conditions. These sediments provide a detailed archive of environmental change. They show that water chemistry was adjusting gradually rather than collapsing abruptly. Reef systems also began to change during the late Frasnian. Fossil evidence shows a gradual decline in the abundance and diversity of stromatoporoid and coral reef builders. Reef frameworks became less extensive over time. This decline did not occur everywhere at once. Some reef systems persisted longer than others, while certain regions saw earlier reductions. The pattern reflects a slow, uneven shift rather than a sudden disappearance. Sediment layers associated with reef decline often show increased input of fine material. This suggests changes in water clarity and circulation. Reduced carbonate production is recorded as reef growth slowed. These changes altered the physical structure of marine habitats. Areas once defined by rigid frameworks transitioned towards softer, more open seafloors. The transformation was measured and progressive. Despite these shifts, many marine organisms continued to thrive. Fossil assemblages from this interval still show diverse communities. Placoderms, ammonoids, and other marine life remained present across wide areas. The changes beneath the surface did not immediately disrupt the entire ecosystem. Instead, they introduced new gradients and regional differences within the ocean. Life adapted within these changing conditions for extended periods. The water column itself became more layered in certain regions. Evidence from sediment chemistry suggests stronger stratification between surface and deeper waters. Reduced mixing limited oxygen transfer in some basins. This stratification developed gradually and persisted intermittently. It did not affect all depths equally. Shallow shelf waters often retained more stable conditions compared to deeper, enclosed basins. These internal changes influenced how energy and nutrients moved through the ocean. In some areas, organic matter accumulated more readily at depth. In others, circulation continued to distribute oxygen and nutrients effectively. The Devonian Ocean became a mosaic of conditions rather than a uniform system. Fossil evidence captures this complexity through variation in preserved communities and sediment types. The slow decline of reef systems altered the flow of water along continental shelves. Without extensive reef barriers, currents moved differently across the sea floor. This influenced sediment deposition patterns. Fine particles settled in new areas while others experienced reduced accumulation. These physical changes are preserved clearly in stratigraphic sequences. Each layer records a slight adjustment in the marine environment. For organisms living within these seas, the transformation was gradual. There is no evidence of sudden mass mortality associated specifically with these early changes. Instead, species distributions shifted subtly. Some forms became less common in certain regions while persisting elsewhere. This pattern suggests environmental pressure rather than catastrophic loss. The ocean allowed time for adjustment. The late Frasnian changes were not isolated events, but part of longer-term environmental trends. Geological records show repeated intervals of oxygen fluctuation and reef stress across this time. Each episode left its mark in the sediment. Together, they chart a slow departure from the earlier stability of the Devonian seas. The transformation unfolded over hundreds of thousands of years. Chemical indicators within sediments reveal changes in nutrient cycling as well. Variations in carbon and sulfur isotopes suggest adjustments in biological activity and decomposition. These shifts point to altered balances between production and decay. Such changes occurred quietly, without dramatic surface expression. The ocean continued to appear calm even as its internal processes evolved. Fossils preserved from this interval often show continuity in form and behavior. Dunkleosteus and other marine organisms remained present through much of the late Frasnian. Their continued existence indicates that environmental changes were within tolerable limits for extended periods. Adaptation occurred through persistence rather than sudden transformation. The sea remained livable, though increasingly complex. Sediment layers act as a slow-moving record of these changes. Each layer represents time passing particle by particle. Differences between layers show trends rather than sharp breaks. The story they tell is one of gradual transition. Conditions shifted, stabilized, and shifted again. The ocean was adjusting its internal balance. Reef decline also affected the distribution of habitats. With fewer rigid structures, some organisms relocated to different zones. Open basins expanded in influence. Shelf environments became more uniform in certain regions. These changes influenced how species interacted without eliminating diversity entirely. The ecosystem restructured itself slowly. The Devonian Ocean during the late Frasnian was neither collapsing nor static. It was changing in measured ways. Oxygen levels varied, reefs diminished, and sediment patterns evolved. These changes did not end marine life immediately. Instead, they reshaped the framework within which life existed. The sea was transforming layer by layer. Within this changing environment, marine organisms continued their lives. Feeding, movement, and growth proceeded within new conditions that developed gradually. The ocean did not demand immediate response, it allowed time for adjustment. Fossil evidence shows continuity across these changes, linking earlier stability to later transformation. The late Frasnian marks a period of transition recorded beneath the surface of the sea. Sediments, chemistry, and fossils together reveal an ocean in slow motion. The transformation was subtle, persistent, and widespread. Life continued as the environment shifted around it. These changes set the stage for later events without announcing themselves loudly. The Devonian Ocean moved forward quietly, carrying its inhabitants through altered waters. The surface remained calm, while beneath it, the balance of the sea slowly evolved. As the Devonian period progressed toward its later stages, marine ecosystems entered a phase of gradual decline recorded carefully in the fossil record. This decline did not occur as a single moment, but unfolded over extended geological intervals. Stratigraphic layers from the late Devonian show progressive changes in species composition rather than abrupt disappearance. Many marine groups that had persisted for millions of years began to diminish in abundance. The ocean did not collapse suddenly. Instead, it slowly released forms that had long defined its structure. The late Devonian extinction events affected a wide range of marine organisms. Reef-building communities were among the earliest to show sustained reduction. Stromatoporoids and corals that once formed extensive reef systems became less common through successive layers. Their frameworks thinned and eventually ceased to dominate shelf environments. This decline altered habitat structure across large areas of the sea floor. The loss of reefs reduced environmental complexity, reshaping how marine communities were organized. Placoderms, once widespread and diverse, were also affected. Fossil records show a steady reduction in placoderm diversity leading toward the end of the Devonian. By the close of this period, placoderms, including Dunkleosteus, disappear entirely from the fossil record. Their absence is not marked by a single boundary but by a sequence of diminishing occurrences. Each successive layer preserves fewer remains, indicating a drawn-out process rather than sudden extinction. Dunkleosteus itself is last recorded in late Devonian strata. Its cranial armor, once common in marine deposits, becomes increasingly rare. Eventually, these remains no longer appear. This disappearance reflects broader patterns affecting large marine vertebrates. The loss was gradual, consistent with environmental pressures accumulating over time. The fossil record preserves this change without evidence of abrupt catastrophe localized to a single moment. Environmental stressors underlying the late Devonian decline were varied and regionally expressed. Oxygen fluctuations intensified in some marine basins, reducing habitable space for many organisms. Geochemical evidence indicates repeated episodes of reduced oxygen availability at depth. These conditions placed pressure on marine life adapted to stable, well-oxygenated environments. The stress did not eliminate life immediately, but narrowed the range of tolerable conditions. Changes in nutrient cycling also reshaped ecosystems. Sedimentary records show shifts in organic matter accumulation and decomposition. These changes altered food availability across trophic levels. Primary production remained present but was redistributed unevenly. Some regions experienced increased organic deposition while others saw reduced productivity. This unevenness affected long-established feeding relationships within the marine web. Sea level fluctuations further influenced marine habitats. While sea levels remained generally high, intervals of regression reduced shallow shelf areas in some regions. The contraction of these habitats removed spaces that had supported diverse communities. Organisms adapted to broad shelves faced reduced living space. This environmental compression intensified competition without producing sudden collapse. Climate variability contributed additional pressure. Although the Devonian climate remained broadly warm, evidence shows increasing instability toward its end. Temperature gradients strengthened in some regions. Ocean circulation patterns adjusted in response. These changes influenced oxygen distribution and nutrient flow. The cumulative effect reshaped marine environments slowly but persistently. As environmental conditions shifted, ecosystems reorganized. Some groups declined while others persisted or later diversified. The extinction was selective rather than total. Placoderms vanished, but other fish groups survived and later expanded. This pattern indicates ecological replacement rather than wholesale loss. The ocean continued, but with a different composition. The disappearance of placoderms marked a major transition in marine vertebrate history. For much of the Devonian, they had been prominent components of marine ecosystems. Their loss removed an entire structural group from the ocean. Fossil assemblages above the extinction intervals reflect this absence clearly. New communities formed without armored fishes occupying the same roles. The extinction unfolded across multiple pulses rather than a single event. Stratigraphic evidence supports several intervals of increased turnover. Each pulse reduced diversity further. Recovery between pulses was limited. Over time, cumulative losses reshaped marine life profoundly. This pattern of stepwise decline is well supported by fossil distributions and sedimentary records. As familiar forms vanished, the seas became quieter in a literal sense, preserved through sedimentation. Fewer large skeletal remains accumulated. Reef structures no longer dominated carbonate platforms. The seafloor recorded simpler assemblages. The reduction in biological complexity is visible in rock layers formed after the extinction events. The ocean did not empty, but it changed character. For organisms that persisted through this interval, life continued under altered conditions. Feeding, growth, and reproduction adjusted to new environmental limits. Fossil evidence shows survival of some lineages that would later expand in subsequent periods. The extinction cleared ecological space without ending marine life itself. The late Devonian decline represents a turning point rather than an ending. The ocean remained active and inhabited, water continued to circulate, sediments continued to settle, and life continued to adapt. The disappearance of Dunkleosteus and its relatives marks the close of a long chapter in marine history. The seas that followed were shaped by the absence of placoderms. Their armored forms no longer moved through open water. Instead, new groups would eventually occupy some of the ecological roles they left behind. This transition unfolded gradually, guided by environmental conditions rather than sudden disruption. Fossil evidence preserves the late Devonian decline with clarity and restraint. There are no signs of chaos, only steady change. Layer by layer, the record shows reduction, disappearance, and replacement. The ocean adjusted over time, maintaining continuity even as its inhabitants changed. The extinction events did not erase the Devonian world in a single motion. They altered it slowly, allowing time for response and adaptation. The sea did not collapse into silence, but its rhythms softened. Familiar forms faded, and new patterns began to emerge. As Dunkleosteus vanished from the waters, it left behind no direct successors of its kind. Its absence is permanent within the fossil record. Yet the ocean itself endured. The late Devonian decline reshaped marine life, but it did not end it. The seas continued forward, carrying the memory of what had been within layers of stone. In this long transition, the ocean grew quieter not through emptiness, but through change. The loss of familiar shapes altered the balance of life. The Devonian world moved gently toward a new state. The extinction unfolded without urgency, marking the close of one ancient order and the slow preparation for another. After the disappearance of Dunkleosteus from the fossil record, the Devonian seas did not remain empty. Marine environments continued, shaped by processes already in motion before the extinction events concluded. Sediment layers above the last occurrences of placoderms record continuity rather than collapse. Water still covered the continental shelves, currents still moved slowly, and ecosystems reorganized within the spaces left behind. The ocean carried on, adjusting quietly to a changed composition of life. With placoderms gone, ecological niches within open marine systems became available. Fossil evidence shows that other fish groups began to occupy these roles over time. Early cartilaginous fishes, represented by sharks and their relatives, diversified in form and distribution. Their remains appear more frequently in post-Devonian strata, preserved through teeth, fin spines, and occasional skeletal elements. These fishes expanded into open water habitats previously shared with placoderms. Their bodies were built differently, but they moved through similar spaces. Bony fishes also underwent significant diversification after the Devonian. Fossil records from later periods show increasing variety among ray-finned and lobe-finned fishes. Their skeletal structures, composed largely of internal bone rather than external armor, allowed different modes of movement and growth. These fishes occupied a range of habitats from open water to near the sea floor. The expansion of bony fishes reflects gradual ecological replacement rather than sudden takeover. The absence of Dunkleosteus marked the end of one lineage, but not the end of large marine vertebrates. Other fishes adapted to open water life increased in abundance. Their fossils show that size and ecological influence were redistributed among new groups. This redistribution unfolded over millions of years. The fossil record does not show an immediate filling of all niches, but a gradual increase in diversity and complexity. Reef systems, which had declined during the late Devonian, later re-established in altered forms. Fossil evidence from subsequent periods shows new reef-building organisms contributing to carbonate structures. These reefs differed in composition from Devonian systems but served similar ecological functions. They slowed water movement, created habitat complexity, and supported diverse communities. The ocean rebuilt its structural framework slowly, adapting to new biological contributors. Sedimentary records show renewed carbonate deposition in many regions following the extinction intervals. This indicates a return to conditions favorable for reef growth and stable marine chemistry. Reef systems did not replicate their Devonian predecessors exactly. Instead, they reflected the organisms available in the post-extinction world. The seafloor once again developed relief and structure, supporting layered ecosystems. Ocean circulation patterns continued to evolve. With changing continental positions and climate trends, currents adjusted gradually. These changes influenced nutrient distribution and oxygen levels. Fossil assemblages record shifting community structures aligned with these adjustments. The ocean remained dynamic, but not chaotic. Its long history continued through adaptation rather than disruption. The disappearance of Dunkleosteus did not erase its influence entirely. Its absence reshaped predator-prey relationships and opened pathways for other fishes to expand. Fossil evidence shows that later marine systems operated under different balances. Energy flowed through new trophic arrangements, shaped by the anatomy and behavior of surviving groups. These systems remained stable enough to persist across long geological intervals. Early sharks expanded into a variety of ecological roles. Some occupied open water zones while others remained closer to the sea floor. Their flexible skeletons allowed different swimming strategies. Fossil distributions indicate wide geographic ranges. These fishes became enduring components of marine ecosystems, continuing into later periods without interruption. Bony fishes, particularly ray-finned forms, began a long trajectory of diversification. Their fossils show increasing specialization in body shape and function. This diversification unfolded gradually, supported by stable marine environments. The absence of armored placoderms reduced competition for certain resources. New strategies emerged within the evolving ocean. Despite these biological changes, the physical character of the ocean remained familiar. Water depths varied across shelves and basins, light penetrated upper layers, and sediments settled slowly. The sea retained its layered structure. Fossil evidence shows continuity in depositional patterns even as biological communities changed. The ocean's long rhythms persisted. The memory of Dunkleosteus is preserved only in stone. Its armor plates remain in older layers, marking a time when placoderms dominated certain marine spaces. Above those layers, its absence is clear. The ocean did not restore that form. Instead, it moved forward with different inhabitants. This transition reflects the irreversible nature of extinction within Earth's history. Marine life after Dunkleosteus was shaped by both loss and opportunity. Extinction removed entire lineages, but it also altered the conditions under which survivors evolved. The fossil record shows gradual rebuilding rather than abrupt replacement. Ecosystems reassembled piece by piece, guided by environmental conditions and available forms. Reef-associated communities expanded again as structural habitats returned. Open water ecosystems adjusted to new dominant fishes. Benthic environments continued to host invertebrates and bottom-dwelling vertebrates. Each zone developed its own balance. The ocean supported this diversity through stable physical processes. The long history of the sea continued uninterrupted by any single species disappearance. While Dunkleosteus no longer swam these waters, the ocean remained active and inhabited. Its currents still moved across the globe, its sediments still accumulated, and its life continued to evolve. Fossil evidence captures this continuity clearly. Over geological time, new patterns replaced old ones. The Devonian world gave way to new marine configurations. The absence of placoderms became a defining feature of later oceans. Yet the sea itself did not diminish. It adapted, carrying forward the legacy of change recorded in stone. In the ocean after Dunkleosteus, life proceeded without memory. New fishes moved through spaces once occupied by armored forms. Reef systems rebuilt under different architects. Energy flowed through new pathways. The sea continued its long story, shaped by time rather than individual presence. The extinction of Dunkleosteus marked the end of a chapter, not the end of the ocean. Its waters remained deep and expansive. Change unfolded slowly, as it always had. The marine world moved on, quiet and continuous, carrying the imprint of past life within its layered sediments and drifting steadily forward through Earth's deep and enduring history. Dunkleosteus is known today through fossils preserved within layers of shale and limestone that once formed ancient sea floors. These rocks accumulated slowly beneath calm Devonian waters, capturing moments of burial without disturbance. Fine sediments settled gently around fallen remains, protecting them from erosion and movement. Over time, pressure and mineralization transformed these sediments into stone. Within this stone, the forms of ancient marine life were sealed and held in place. Dunkleosteus entered the fossil record through this quiet process. Shale deposits preserving Dunkleosteus formed from very fine particles that settled in low-energy environments. These environments were often deeper shelf settings where water movement was minimal. The fine grain of shale allows delicate surface features to be retained. Armor plates preserved in shale frequently show clear outlines and subtle textures. Growth lines, sutures, and attachment points remain visible. This level of detail reflects burial that occurred without strong currents or physical disruption. Limestone deposits also preserve Dunkleosteus fossils. Limestone forms primarily from accumulated carbonate material, often derived from skeletal remains of marine organisms. These deposits indicate warm, clear waters where carbonate production was active. Dunkleosteus armor preserved in limestone is often encased within dense rock, requiring careful preparation. The chemical stability of limestone helps protect bone from deformation. Together, shale and limestone provide complementary records of Devonian marine environments. The position of Dunkleosteus fossils within these rocks reveals information about ancient seabeds. Many specimens are found lying flat, suggesting they settled gently onto the sea floor after death. There is little evidence of transport over long distances. The orientation of plates often remains natural rather than scattered. This indicates quiet burial conditions. Such conditions are consistent with calm shelf seas documented for much of the late Devonian. Preparation of Dunkleosteus fossils requires precision and patience. Tools are used to remove surrounding rock without damaging the bone. Preparation reveals fine surface details that are not visible when the fossil is first exposed. These details include textures formed during growth and wear. Edges of armor plates show the shape and thickness of bone. Each prepared specimen adds clarity to understanding the animal's anatomy. The preparation process also reveals how plates fit together. Articulated specimens show the relationships between cranial and thoracic elements. This information allows accurate reconstruction of the head shield. Without careful preparation, these relationships would remain hidden. Fossil preparation transforms stone-bound remains into readable records. The process itself respects the slow pace at which the fossils formed. Museums around the world curate Dunkleosteus fossils. These institutions preserve specimens collected from various geological formations. Each fossil is catalogued with information about its origin and context. Collections allow comparison between individuals from different regions. Through this comparison, consistent anatomical features are identified. Museums serve as long-term guardians of these remains. Curated fossils are stored in controlled environments to prevent deterioration. Temperature and humidity are managed carefully. This ensures that bone and surrounding rock remain stable. Researchers study these specimens over many years. New techniques can be applied without damaging the original material. The fossils remain available for future study, extending their scientific value. Exhibits displaying Dunkleosteus fossils present the animal within its geological context. Armor plates are often mounted to show their original arrangement. Accompanying information explains the age and environment of the fossils. These displays do not recreate movement but present structure. Visitors encounter stone records rather than living reconstructions. The emphasis remains on what is preserved. Stone holds the memory of ancient seas through these fossils. Each layer of rock represents time passing in small increments. Dunkleosteus fossils are embedded within these layers as markers of a specific interval. The stone records not only the animal but the conditions of burial. Grain size, mineral content, and layering all contribute to this record. Together, they preserve a snapshot of Devonian marine life. Fossil sites yielding Dunkleosteus are often carefully protected. Excavation proceeds slowly to avoid damaging surrounding material. Each discovery adds to a broader picture built over decades. Individual fossils are rarely complete, but together they form a comprehensive record. The stone does not preserve motion, only form. Yet form alone carries significant information. Through fossils, Dunkleosteus exists as an arrangement of plates and surfaces. The absence of soft tissue does not erase its presence. Bone alone provides enough evidence to reconstruct anatomy and growth. Stone preserves what water once supported. The transition from living animal to fossil occurred without urgency, guided by sediment and time. Limestone and shale differ in appearance, but both contribute to preservation. Shale often splits along fine layers, revealing fossils in profile. Limestone may require cutting and polishing to expose detail. Each method reveals different aspects of the fossil. Together they enrich understanding of ancient marine conditions. The global distribution of Dunkleosteus fossils reflects widespread Devonian seas. Similar fossils appear in rocks now separated by continents. This distribution confirms the connectivity of ancient oceans. Museums holding these fossils connect distant regions through shared history. Stone records these connections clearly. Over millions of years, tectonic forces lifted seabeds into mountains and plains. Fossils traveled upward with the rock. What was once deep water became accessible land. Dunkleosteus fossils emerged from stone long after the animal itself disappeared. This emergence is part of Earth's ongoing geological cycle. The fossils do not change once formed. They remain fixed within stone until uncovered. Their stillness contrasts with the movement of the ancient sea, yet they preserve evidence of that movement indirectly. Armor shape reflects life in water, even when held in rock. Stone does not forget. It holds impressions, layers, and structures across vast spans of time. Dunkleosteus exists now only as part of this memory. Each fossil is a quiet reminder of ancient seas that no longer exist. Through stone, the Devonian Ocean remains present. When viewed together, these fossils form a record without sound or motion. They rest in drawers, cases, and displays, yet their presence is complete. Stone carries the weight of time without change. Dunkleosteus remains within it, preserved exactly where ancient waters left it, held calmly in the enduring memory of rock. The Devonian Sea settles into stillness as time continues its quiet passage. Water spreads across broad basins where life once moved in layered currents. These basins now rest beneath calm surfaces shaped by sediment and depth rather than motion. The ocean remains present, filling space without urgency. Its structure endures even as its inhabitants change. This sea is not empty, but it is unhurried, holding the memory of earlier worlds within its depths. Water layers drift slowly above the ancient seabed. Differences in temperature and density create gentle stratification that changes little over long intervals. Upper waters receive light that softens as it descends. Below, dimmer layers remain stable and cool. These layers do not mix rapidly. They rest upon one another in quiet balance. The Devonian Ocean was defined by this order, where movement occurred without turbulence. The basins beneath these waters are wide and continuous. Sediment settled here over immense spans of time, forming the rock record preserved today. Each particle descended slowly, guided by gravity and calm currents. There were no sudden collapses or violent shifts in these settings. The seabed accumulated its layers patiently. These basins became archives, holding evidence of past life and past conditions without interruption. Time continues in this ocean without disturbance. Geological processes operate steadily, not in bursts. Sedimentation, compaction, and mineralization proceed at rates measured in millimeters per 1,000 years. This pace allows preservation rather than erasure. The Devonian Sea did not rush forward. It allowed each moment to settle before the next arrived. The passage of time became part of the structure of the ocean itself. The calm of this sea is reflected in the uniformity of many sediment layers. Fine laminations show little sign of disruption. Fossils remain where they settled. The absence of chaotic mixing indicates sustained tranquility. Even when life declined or changed, the physical environment maintained its steady rhythm. The sea absorbed change without breaking its continuity. Vastness defines the Devonian Ocean as much as calm. Continental shelves extended far from ancient shorelines. Water covered immense areas of the planet's surface. These expanses connected distant regions through shared conditions. Marine environments were not isolated pockets but parts of a global system. The sea's scale allowed stability, distributing heat and nutrients evenly across wide areas. Within this vastness, the absence of former inhabitants becomes noticeable only through the fossil record. Dunkleosteus no longer moves through these waters. Placoderms no longer occupy open basins. Their absence does not create emptiness, but silence in the record of form. The sea itself remains unchanged by the loss. It continues to hold space without regard to which organisms fill it. The Devonian Ocean endures beyond individual lifetimes and species. Its processes outlast generations. Water cycles, sediment deposition, and chemical balances persist regardless of biological turnover. This endurance is captured in rock layers that extend beyond extinction boundaries. The sea does not pause or reset. It flows forward, carrying continuity through change. Light continues to filter through the water column, though the life that once responded to it has altered. The physical behavior of light remains consistent. It scatters, weakens, and fades with depth. This pattern defines the ocean's vertical structure. The Devonian Sea retains this structure even as its communities evolve. Physical laws remain constant while life adapts. The quiet of the sea is not the absence of motion, but the presence of slow motion. Currents move gently along basin contours. Water exchanges occur gradually. These movements do not announce themselves. They shape environments over long periods. The Devonian Ocean was shaped more by patience than force. Sediment continues to accumulate on the seabed. Even after major biological changes, deposition proceeds. New layers cover old ones, sealing records of earlier worlds. Each layer becomes part of a growing archive. The sea floor deepens in time, not through collapse, but through addition. This slow burial preserves the story of the ocean without erasing it. The enduring nature of the Devonian Sea allows it to be understood as a whole rather than as moments. Fossils capture fragments, but the sea itself provides continuity. Water, rock, and time interact steadily. This interaction does not depend on dramatic events. It persists through ordinary processes repeated endlessly. The ancient deep holds no urgency. Its vastness absorbs change. Species appear and disappear, yet the sea remains. Its calm is not fragile. It is maintained by scale and duration. The Devonian Ocean demonstrates how environments can persist through biological transformation without losing their identity. Even as geological periods transition, the sea maintains its presence. Boundaries in time are marked by changes in fossils, not by changes in water itself. The Devonian Sea flows into the next interval without pause. Its character evolves slowly, shaped by shifting continents and climate. Still, its fundamental calm remains. The memory of the Devonian Ocean is carried forward in stone and structure. Layers record its depth, chemistry, and stillness. These records do not fade quickly. They remain accessible millions of years later. The sea's endurance allows its story to be read long after its surface has changed. In this settled state, the Devonian Sea becomes a backdrop rather than a stage. It supports, records, and outlasts life. Its calm allows preservation, its vastness allows stability, its endurance allows continuity. The sea does not conclude, it continues, indifferent to endings. The ancient deep holds the final rest of this story. Water covers the basins quietly. Time moves forward without disturbance. The Devonian Ocean remains calm, vast, and enduring. Its presence is steady, its rhythm unbroken. The story rests here, not as an ending, but as a pause held gently within the depths of ancient water.